In this talk, I want to spend some time thinking about the toughest problems we face in creation geology. What are some of the encouragements? What are some of the challenges? And what approach should we take to answering hard questions? I want to begin by telling you a bit about my own story. I think I was always interested in rocks and fossils. Like lots of other boys, I loved dinosaurs and I enjoyed reading books on the history of life, full of lost worlds and long vanished animals and plants. When I was about 10, I became a Christian. A friend invited me to a youth club run by the local evangelical church, and that year I went along to their summer camp. That was where I became a Christian, and not long afterwards my mum and dad became Christians too. It must have been around that time that I first encountered creationism, reading literature like Sylvia Baker's Bone of Contention and eventually the Genesis Flood. I became convinced that young age creationism was biblical, and I started to become familiar with some of the basic arguments. But it wasn't until the mid-80s, when I began to study geology more formally, that I really began to encounter problems. As an undergraduate from 1987 to 1990, I was confronted with data and interpretations of the data that I'd never had to face before, and it was profoundly unsettling. Many of the things I was being taught seemed to present real challenges for the biblical view of Earth history, especially the idea of a young Earth and a global flood, and I didn't always have good answers to these problems. One problem I remember being particularly exercised about was the time needed for the formation of granite bodies. Granite is a crystalline rock made up of the minerals quartz, feldspar and mica. It's an igneous rock which formed by the cooling of a hot magma. More specifically, it's an intrusive igneous rock, which means that it was emplaced at some depth below the Earth's surface. Granite typically occurs in large bodies called batholiths, made up of many individual granite intrusions called plutons. On one student field trip, we were taken to see outcrops of the enormous granite batholith that underlies the southwestern peninsula of England. You can see outcrops of the granite at Dartmoor, Bodmin Moor and Land's End, as well as on the Isles of Scilly. It's thought to have been emplaced in the lower Permian, and it intrudes into older Paleozoic rocks. On another occasion, we were taken to see the Shap Granite in the northwest of England. This is a smaller body, about 5.5 square kilometres in outcrop, though it's part of a larger body subsurface. It was emplaced in the lower Devonian, and it intrudes into older sedimentary rocks and volcanic deposits. So where did the magmas that crystallised into these granite bodies come from? Well, the story of granite formation that I learned as a student starts about 20 miles or so below the Earth's surface, where the partial melting of lower crustal rocks generates the granite magmas. And because the granite magmas are so thick and viscous, extracting them from the partially melted parent rocks was thought to be quite a slow process. Once extracted, the hot magmas are thermally buoyant, and they have a tendency to rise upwards through the crust, and it was thought they moved through the crust in enormous balloon-shaped bodies called diapirs, a bit like the rising blobs of lava in a lava lamp. The magma literally had to force its way through the crust, making space for itself as it moved upwards. And this process also took time. Some suggested perhaps 150,000 years or so for the magma to make its way from the lower crust to a place of thermal equilibrium in the upper crust, where it would begin to collect to form plutons. And then, once it was in the upper crust, the granite magma would slowly cool and crystallise, eventually becoming a solid igneous rock. But granite bodies like the one beneath southwest England are so big that it was assumed it would have taken hundreds of thousands or even millions of years for them to cool down. And even that's not the end of the story, because once emplaced, the granite would still be buried under 3 to 6 miles of rock. Another few million years of gradual erosion would be needed to strip away the rocks above the granite body so that it could be exposed at the Earth's surface where we see it today. In other words, very long time spans were required for the process of granite formation. And as a young geology student, I just couldn't see how it could possibly be done within the short time frame given in the Bible. Even worse, other Christians were also telling me that this was a problem. I was reading more widely than before, including books and papers that were critical of young age creationism. One of the books I read was by Davis Young, an expert on igneous rocks and an evangelical Christian. And he pointed to the formation times of large igneous bodies like granite batholiths as evidence against a young Earth. He said of the long time spans required, "These figures are not figments of some scientist's imagination. They have not been conjured up to fit into some preconceived theory of the Earth. Their estimates arrived at by applying to measurable or reasonably inferred properties of rock and mineral materials a mathematical theory of heat conduction in solids and liquids that holds true for materials today." Well, all of this was enough to keep a young creationist student awake at night. So what did I do? Well, the first thing I did was to look for answers. And I came across one creationist, Robert Gentry, who was thinking about granites, and in particular the microscopic spheres of radiation damage called radiohalos that we find in some granite minerals. Now, without getting bogged down in the details, what Gentry had to say was intriguing because the radiohalos he was describing really did seem to pose some problems for the conventional understanding of granite formation. However, Gentry's studies of the radiohalos had led him to conclude that all granites must be creation-weak rocks, rocks that had been directly created by God in a cold, solid, crystalline state. And I knew that couldn't be right, because I'd seen for myself how granite bodies intruded into fossil-bearing sediments, and how thin veins of granite even extended outwards from the granite bodies into fractures and weaknesses in the surrounding fossil-bearing rocks, such as you can see in the photo here. That meant the granites had to have been emplaced in a molten state, and they had to be younger than the fossil-bearing sediments into which they were intruded, sediments that presumably were deposited during the flood, or even in some cases after the flood. There was even evidence that the heat from the granite magmas had cooked the sediments into which the granites were intruded. And for some granites, there were really severe constraints on the timing of emplacement. For example, the Shap Granite, which I'd seen in the north of England, had been intruded into Ordovician and Silurian age rocks, but it must have been uplifted and unroofed by erosion by the lower Carboniferous, because only half a mile from the place where the granite was being quarried, there was a streambed exposure in which you could see pebbles of the granite in a conglomerate at the base of the lower Carboniferous limestone. So this granite body had to have been emplaced, uplifted, and eroded within, days, weeks during the flood. But how? I really didn't have any good answers. There was one glimmer of light. In 1987, I joined the Biblical Creation Society here in the UK, and they had an Earth Science group. It wasn't very active when I joined, but in previous years it had been, and they had a back catalogue of circulars on various Earth Science topics. And a couple of those articles were on the topic of granite formation. One was about recent laboratory research documenting the rapid growth rates of crystals in cooling magmas, and the other was about the role that convection might have played in reducing the cooling times of large igneous bodies. So it was all very interesting, but still granite formation seemed a big problem to me. And as if granite formation wasn't bad enough, it was just one in a long list of problems that I was encountering as I studied geology. I also learned about fossil reefs that would have required long time spans to grow in place, desert sandstones that couldn't possibly have been deposited during a worldwide flood, sediments such as chalks and mudstones that required slow depositional rates, regional metamorphism that required long timescales for the precursor rocks to be deeply buried, heated and exhumed, not to mention a whole host of problems connected to radiometric dating. It would have been very easy to get overwhelmed. And that's what I think happens to a lot of creationist students. Perhaps they've been raised in Christian homes. They go to church. They've been taught what the Bible says about creation. But then they go off to university and they meet problems and intellectual challenges they haven't met before. They're away from home and from all of their usual support networks, perhaps surrounded by people who don't share their biblical perspective. And by the time they finish university, many of them aren't young-age creationists anymore. And let's be frank, it is easier to take the path of least resistance, to go with the intellectual flow and to say, well, I must have misunderstood the Bible. After all truth is God's truth, right? So if the rocks and the fossils are telling me that the world is billions of years old and there never was a worldwide flood, well then the problem must be with my interpretation of Scripture. And so we look for ways to reinterpret the Bible to accommodate conventional thinking about an old earth and evolution. Sadly, some go even further and end up abandoning the Christian faith altogether. They just can't find a way to reconcile what the Bible says with the things they're learning at university, and so they walk away. Well, for whatever reason, that wasn't the path I took. I decided I was going to stick with the Bible come what may. I knew what Scripture said about creation and the flood, and I believed that it was true. God surely understood more than I did, and that meant I had to trust him even when the answers I was looking for remained elusive. I don't think I had this particular scripture in mind at the time, but looking back now it seems appropriate. Habakkuk chapter 3, verses 17 to 18. Although the fig tree shall not blossom, neither shall fruit be in the vines, the labour of the olive shall fail, and the fields shall yield no meat. The flock shall be cut off from the fold, and there shall be no herd in the stalls. Yet I will rejoice in the Lord. I will joy in the God of my salvation. I had to trust God, even in the face of things I really didn't understand. Of course, that makes it sound as if I had no reasons to trust what the Bible said about creation and the flood, and that certainly wasn't the case. There were lots of things I didn't understand, but there were also lots of things I learned in my studies that helped to confirm what the Bible said. I remember, for example, one day talking with one of my lecturers about the Silurian fossil beds we'd recently seen on a field trip. They were interpreted as ancient seafloors preserving the remains of animals where they'd been living. But the fossils were all broken and had clearly been washed in by water. I pointed this out, and the lecturer agreed with me. These were not normal seafloors, he said. Of course, in the back of my mind, I was thinking about the flood. On another occasion, we were talking about graptolites, a group of extinct animals that live in colonies. And the lecturer said something very interesting. He said he didn't really see any compelling evolutionary series in the graptolite fossil record. And he was in a position to know because he'd studied the graptolite fossil record for his PhD. Well, moments like these made me think perhaps it wasn't so crazy to be a creationist after all. During that time, I had to learn some important lessons. To hold on to God and to his word, even when faced with things that I found perplexing. To be honest about the data and the challenges it presented without allowing myself to be overwhelmed by it. And to seek new ways of understanding the world that were consistent with both the scientific data and with the Bible. And I believe those lessons stood me in good stead. In fact, they're helpful lessons in the life of faith generally, not just in the way we think about scientific challenges. I came to realise it was okay to have unanswered questions. In fact, science is really fun precisely because we have all of those unanswered questions. And in the years since then, it's become even clearer to me that we should see those unanswered questions as opportunities. Opportunities that God has given us to explore his creation and his word more carefully, to deepen our faith and to get to know him better. Another intriguing thing is that since my student days, I've had the opportunity to see many of the questions I had back then being answered, even sometimes by research that's being done by conventional geologists. For example, conventional thinking about granite formation, one of those hard problems I really grappled with as a student, has undergone a complete shake-up over the last few decades, and geologists have now called into question virtually every aspect of what I'd once been taught. Remember I said that granite magmas are formed by the partial melting of rocks in the lower crust, and that the extraction of those magmas from the parent rocks was considered a slow process because the magmas were so viscous. Well, we now know that the presence of water in the lower crust significantly lowers the temperature required to melt the parent rock, making the production of magmas much easier. And water also dramatically reduces the viscosity of the magmas. We now know that even the driest granite magmas are orders of magnitude less viscous than previously thought, and that reduces the estimated extraction times to only centuries or even decades. Another major shift in thinking concerns the movement of granite magmas through the crust. The traditional view that the magmas had risen slowly as huge balloon-shaped bodies had always faced a problem, which was how to accommodate those enormous bodies within the solid crust. Some geologists began to suspect that the magma in fact rose rapidly through the Earth's crust along narrow fractures, a process that was up to 1 million times faster. At rates like this, it would have taken only a few days or weeks for granite magmas to make their way through the Earth's crust, and the filling of granite plutons could have happened quite quickly. In fact, studies of the minerals found in some granite bodies have helped to confirm these rapid rates of ascent. Epidote crystals in granites in Colorado indicated that the magma must have been transported through the crust in less than 50 years. The reasoning goes like this. Epidote crystals are stable only at very high pressures, and so they must have formed while the magma was still very deep in the crust of the Earth. But if the magma had travelled upwards very slowly, the epidote crystals would have become unstable and eventually dissolved in the magma. The only way they could be preserved at the surface is if they were carried along with the magma very rapidly. And what about the time that was needed for large granite bodies to cool down after they were emplaced? Well, most of the older estimates of cooling times, including those that Davis Young was relying on, were based on conductive heat loss from the granite magmas to the surrounding rocks, and that was undoubtedly a slow process. But geologists began to realise that the circulation of water within and around a granite body, in other words a convective system, would have been much more efficient at removing heat, cooling the granite much faster than by conduction alone. And what's more, seismic studies showed that most individual granite plutons are tabular in shape. They lack deep roots, and their sheet-like shape gives them a very large surface area through which heat can be rapidly lost. It's likely that in many cases the circulating waters that help to cool the granite body also played a part in bringing it rapidly to the Earth's surface. The hot magma would have caused the surrounding groundwater to flash to steam, resulting in violent steam explosions, and these would have helped to break up the rocks around the granite body, accelerating their erosion and removal. I don't think we've solved every problem concerning granite formation, but I think it's fair to say that it seems a much less formidable problem now than when I was first thinking about it as a student 30-odd years ago. And I haven't even touched on Andrew Snelling's work on radio halos, which builds on Robert Gentry's work but puts it into a more convincing geological framework. In fact, the first couple of days I ever spent working full-time for Biblical Creation Trust, or Biblical Creation Ministries as it was known then, was spent with Andrew travelling up to the northwest of England to collect samples of the Shap Granite for his radio halo work. And you can read about the results of that work in this 2008 ICC paper. Now, of course, we haven't seen the same kind of progress in every area. Some of the hard problems that I faced as a student are still hard problems. Some have even seemed to get more difficult. But now, when I'm faced with what seems to be an intractable problem, I try to remember the revolution in thinking about granite formation, and I start to wonder whether these other problems might take on a very different aspect if only we had more data and were able to apply some fresh thinking. So what are some of the areas where we still face unresolved problems? For reasons of time, I can only give a couple of examples. But one area where we face some tough challenges is in the area of biostratigraphy. Biostratigraphy is the discipline that uses fossils and fossil assemblages to subdivide and to correlate or match up rock layers. The pioneering geologists of the 18th and 19th centuries were able to work out that there were recognisable successions of rock types. For example, the upper Carboniferous rock layers are well known for the widespread development of coal. The Permian and Triassic layers for the widespread development of red beds, and the upper Cretaceous layers for the common development of chalk. And superimposed on this rock succession, the early geologists recognised a fossil succession. For example, there's an orderly succession in terms of the first appearances of major groups. First, single-celled organisms, then multicelled organisms and invertebrates, then the fish, and then amphibians and reptiles, then mammals and birds. John Baumgartner put it quite well. He said, "We find no archaeocyathids above Middle Cambrian strata. We find no pentamerous brachiopods or cystoid crinozoans or psilopsid plants above Devonian strata. No graptolites above Mississippian strata, and no trilobites or rugose corals above Permian strata. On the other hand, we find no birds or angiosperms in strata lower than Jurassic, no mammals in strata lower than Upper Triassic, no reptiles in strata lower than Pennsylvanian, and no amphibians in strata lower than Devonian. A similar unmistakable sequence of types also exists in the case of the microfossils." Well, what does this fossil succession mean? Most geologists interpret it from an evolutionary standpoint, with the rock layers and their enclosed fossils thought to document the evolution of life over vast eras of time. I hardly need to say that this interpretation of the fossil record stands in stark contrast to what the Bible tells us about the history of the earth and its organisms. Straightforwardly understood, the Bible doesn't allow for the passage of long eras of geological time or the gradual evolution of life. And so creationists have proposed a radically different way of understanding the fossil record. Given that the most geologically significant event in Earth history according to the Bible was the global flood in the days of Noah, creationists typically divide the fossil record into three parts. A part that was formed before the flood, a part that was formed during the flood, and a part that was formed after the flood. Now, there's a lack of consensus among creationists about exactly which parts of the fossil record correspond to which parts of biblical history, but most seem to agree that at least the Paleozoic and Mesozoic sediments were deposited by the flood. Assuming that's correct, the fossils in those sediments can be interpreted as communities of organisms that were successively buried during the flood. As the floodwaters advanced from the oceans onto the land, whole communities would have been picked off, transported, and buried in the order in which they were encountered. And so the resulting sequence of fossils would reflect the ecological distribution of organisms before the flood, rather than evolution over long ages. This idea was first proposed in 1946 by Harold W. Clarke in his book The New Diluvialism, and it's come to be known as the ecological zonation model. In its original form, Clarke proposed a series of pre-flood ecological zones varying in altitude from the deep ocean to the high mountains. More recently, Clarke's model has been modified to propose a series of adjacent or biogeographical provinces rather than elevational provinces. And some of these pre-flood biomes seem to have been very different from anything found on the Earth today. For example, Kurt Wise has reconstructed the fossils buried in the uppermost Precambrian sediments as a community of organisms that was living in a hot spring biome fringing the pre-flood continents. This seems to have consisted of stromatolite mounds forming a kind of barrier reef, protecting a deep water lagoon in which the strange ediacaran organisms lived. Nearer to the shore, there may have been an extensive shallow ocean with trilobites and other marine animals represented today by the fossils of the lowermost Paleozoic. Kurt Wise has also proposed that the plant fossils of the Paleozoic represent the remains of a huge floating forest community, something like a modern quaking bog but on a much larger scale, growing out over the deep pre-flood ocean. Around the edges of the floating forest, there would have been small water-dependent plants. Towards the centre of the forest, the mat of vegetation would have been thick enough to support tree-like ferns and seed ferns, club mosses, horsetails. During the flood, this floating forest community was broken up and destroyed from the outside in, with the central part being buried to form the extensive Carboniferous coal seams. Here's a diagram from my book, The New Creationism, that illustrates this modified biome model. In this model, the cross-bedded sandstones of the Permian probably represent the reworked coastal dunes of the pre-flood world, and the dinosaur-dominated communities of the Mesozoic, some of the inland biomes that were distributed across the pre-flood continents. So an ecological zonation or biome model seems to provide a good explanation of at least the first order or larger scale patterns in the part of the fossil record that was deposited during the flood. However, there are significant unresolved problems. The first of these is that although this model explains some of the first order patterns in the fossil record, the fossil succession is actually much more complex than this. Consider the Mesozoic sediments in which we find dinosaurs alongside some unusual mammals and gymnosperm plants. It's easy for us to think of this as one of those unique pre-flood biomes. But then we notice that the dinosaur assemblages in the Cretaceous sediments are not the same as those in the Jurassic sediments or the Upper Triassic. So perhaps there were multiple dinosaur biomes. And then we look more closely still, and we see that the fossil assemblages in, say, the Upper Jurassic are different to those in the Lower or Middle Jurassic. And within the Upper Jurassic, the fossils of the Oxfordian stage are different to the fossils of the Kimmeridgian stage, and so on. So there's a lot of complexity in these pre-flood biomes that we've hardly begun to understand. Secondly, there's the question of how these ecological communities were transported and buried as whole communities during the flood. Where were these communities originally located? Where were they living? Evidently not in the places where they ended up being buried. So how far were they transported and for how long? And what kinds of sedimentary processes were involved? There are lots of unanswered questions. Thirdly, our models at the moment can't account for fossil organisms that have very narrow stratigraphic ranges. Based on radiometric dates, the average stratigraphic range of a fossil species spans perhaps 1 to 10 million years of radiometric time, some even less than that. Even the average genus rarely exceeds 20 to 30 million years of radiometric time. Evolutionary scientists have an explanation for these narrow stratigraphic ranges, because in their model, organisms change through time, and each layer of rock represents a snapshot of the diversity of organisms that were alive at that particular moment in evolutionary history. Species that lived on the Earth for only a short time interval therefore show up only in rocks deposited during that short time interval. But as creationists, we can't appeal to that explanation because we don't interpret the fossil record in terms of evolutionary change over time. So we have to explain how fossil species came to be deposited within very narrow stratigraphic intervals and in a consistent order across the world by sedimentary processes that were operating during the year of the flood. Consider, for example, the ammonoids and bivalves preserved in the Upper Cretaceous chalks of southern England. These fossils are arranged in an orderly succession that geologists have used to subdivide the English chalk into a series of vertically stacked biozones. But remarkably, that same sequence of biozones, the same stack of fossils in the same order, can be seen in the Cretaceous sediments of western Kazakhstan, almost 4,000 kilometres to the east. How did a global flood manage to pick up these organisms from wherever they were originally living in the pre-flood world, transport them perhaps thousands of miles around the globe, and then deposit them in sedimentary layers over a vast area in a consistent order without mixing them up? In other words, if the order of these fossils represents some kind of pre-flood ecological succession, then how was that succession preserved through the catastrophic events of the flood? So biostratigraphy presents us with some hard problems, to which we don't, as yet, have very good answers. Let's look at one more challenge for the flood model: in situ fossil assemblages. Throughout the geological record, there are fossil communities that appear to have been preserved in the place where they were living. In other words, it doesn't look as though they were transported or washed in. And it seems that these communities would have required more time to develop or to grow than would have been available during the year of the flood. Examples include apparently in situ reef-like structures and carbonate hardgrounds with well-preserved faunas of encrusting and boring organisms. I'm going to focus here on hardgrounds. Hardgrounds are found throughout the geological record, but they seem to be particularly common in Ordovician, Jurassic and Cretaceous sediments. Hardgrounds are conventionally interpreted as stationary surfaces where sedimentation for a time had ceased, the carbonate seafloor had become lithified or hardened, and then encrusting organisms like bryozoans or oysters and boring animals like bivalves and worms had colonised the hardened surface. Hardgrounds like these seem to have required some time to develop. So what are we to make of them? Well, let's look at a specific example. The Middle Jurassic hardground exposed in the vicinity of Vallis Vale in the county of Somerset in southwest England. In this region, a thick sequence of Paleozoic sediments, including the Carboniferous limestone, was folded and then planed off to form a widespread erosion surface that formed the seafloor. Later, in the Middle Jurassic, Oolitic limestones were deposited on top of this erosion surface. But before the Middle Jurassic limestones were deposited, a hard ground developed at the unconformity surface. In this photo, you can see a classic exposure of the angular unconformity that was described in the 19th century by the geologist Henry de la Beche, with the flat-lying cream-coloured Middle Jurassic limestones above and the tilted grey Carboniferous limestones underneath. If we look at the upper surface of the unconformity in side view, we can see some narrow cylindrical borings that extend about 6 inches down into the hard ground surface. These are called triponites, and they're thought to have been made by worms that used an acid or other chemical to dissolve the limestone. We can also see some distinctive bulb-shaped borings called gastrocanalites, thought to have been made by a type of rock boring bivalve. The unconformity surface itself is very smooth, but occasionally there are small ridges that result from resistant chert bands in the Carboniferous limestone. Interestingly, we don't find the triponites and the gastrocanalites borings in the chert ridges, but we do occasionally see a different type of bivalve boring in the ridges, which is thought to have been produced by mechanical means rather than chemically. When we look at the unconformity surface in plan view, in other words from above, we see that there are fossil oysters covering and cementing to this surface. And the oysters often seem to fit together a bit like a jigsaw puzzle, suggesting that as they grew, there was competition for space between oysters that were next to one another. The oysters can reach up to 6 inches across, suggesting they had some time to mature after they colonised the surface. It's even been claimed that there are several episodes of boring interspersed with oyster growth, some say up to 7 successive levels. Now we know that given optimal circumstances, oysters can colonise a surface and grow quite quickly. But still, the amount of biological activity represented here seems quite hard to explain within the single year of the flood. The photos I've just shown you were taken in 1996. Since then, the sites have experienced quite a bit of weathering, and they were much more degraded when I went back to look at them again in 2016. But these photos show the same features. You can still see the burrows and the oysters, although the oysters in particular aren't as well preserved today as they were 20 years ago. Interestingly, very similar hard grounds are present at the same stratigraphic level, in other words in the Middle Jurassic, across the English Channel in Normandy in France, and even in Utah in the USA. Hard grounds can also be seen in Paleozoic rocks, but with crinoids and bryozoans playing the role of the encrusters rather than oysters. So hard grounds seem quite problematic for traditional flood geology, and to my knowledge very few creationists have really studied them in detail. Some preliminary field investigations of Ordovician hard grounds have been carried out, and some fairly speculative ideas put forward to try to account for them, but there's clearly a need for a much more thorough investigation. So as we draw towards the end of this talk, what are we to do when we're faced with these kinds of hard problems? The first thing to say is that we need to be honest about the problems. We make a big mistake if we dismiss the data that seems to support evolution in an old Earth, or if we treat it lightly. There are real challenges to be faced, and in this talk we've looked at just a few of them. However, when we think about the problems, it can be easy to feel overwhelmed by them. Faced with hard problems, some people might be tempted to just throw their hands up in despair and conclude that our task is hopeless, that young age creationism is nothing more than an exercise in wishful thinking. So we need to remember a couple of other things. First, remember that the problems aren't all on our side. Both the creation model and the evolution model have things they explain well and things they explain poorly. If we simply throw in the towel and adopt the conventional evolutionary model, we haven't solved our problems. We've just swapped them for a different set of problems. Secondly, remember the progress we've already made. In this talk, I've dwelt more on the problems we face than on the successes, but make no mistake, there are success stories that need to be told. Today, we have models with great explanatory and predictive power like catastrophic plate tectonics, and research projects like the one that John Whitmore led on the Coconino Sandstone have shown just what can be done when we apply ourselves in a focused way to hard problems. This track record of success, along with my faith commitment to the biblical record, suggests to me that this kind of research really is worth pursuing. One final thing. When you think about the strategy that we employ to solve these hard problems, I want to recommend that we embrace model building. If we're really serious about tackling some of these hard problems, we've got to move beyond simply taking pot shots at evolution. Poking holes in someone else's model won't solve the problems with our own model. And we shouldn't fall into the trap of firefighting problems in an atomistic way either. It's far too easy to leap onto a solution to problem X without any thought as to how that impacts areas W, Y, and Z. What we need is not just an apologetic to get us out of an immediate difficulty. We need a whole new model that explains the data in an integrated way. Of course, some will say that the efforts to build these kinds of creationist models are a fool's errand. They'll say that evolution and an old Earth are so well supported that it's simply impossible to replace them. But I think that's intellectually lazy. How will we know whether alternative models can be found unless we're willing to look for them? Others may say, but we have looked. Creationism was tried centuries ago and it didn't work. But again, I think that's a mistake. Serious model building from a creationist perspective is actually quite a new phenomenon. Until relatively recently, creationism was not seriously tried as a professional, multidisciplinary, multi-expert enterprise. Of course, what I'm suggesting is a vast endeavour, one that we've barely begun. But I do believe that if the next generation of creationists, with the Lord's help, takes up this challenge, we will see real progress. If we dodge the challenge, well, we'll still be facing exactly the same hard problems in 10, 20, 30 years' time. It's really down to us.